Hello, in this video I will be going through the topic 6 test review. I'm going to try to go through everything in detail. I know there's a lot of different rules and properties and concepts, so I want to go through it as slow as I can. Starting with number 1, says simplify, and there's a bunch of problems within this one because it's all exponent rules. In letter A, x to the 6th times x to the 4th. The rule for when we multiply exponential terms and they have the same base, since they have the same letter, is that we add the exponents. So x to the 6th and x to the 4th, that makes x to the 10th. So that is the answer for this one, x to the 10th. When we are dividing exponent terms and they have the same base, they have a p on top and a p on bottom, we subtract the exponents. So that's p to the 11 minus 8, which equals p to the 3rd power. C, negative exponent. We do not like negative exponents. They are not allowed in math. How do we fix it? Negative exponents, we change it by flipping it from where it's at on the fraction and then making the exponent positive. So currently it doesn't look like a fraction, but everything can be made into a fraction by putting it over 1. So now you clearly see that x to the negative 5th is on top. Therefore, I'm going to move it to the bottom with a positive exponent. I do need something on top, so I'm going to put the 1. So x to the negative 5th is 1 over x to the 5th. X to the 0 power, this is the easiest exponent rule. Most of you probably have this one down. Anything to the 0 power is 1. E, there is an exponent outside of the parentheses. Parentheses should mean to us distribute, so I'm multiplying these numbers. So when I distribute that, I get a to the 12th, b to the 20th. Notice, I'm just going to quickly explain that I cannot add these two exponents. Because they have different bases, this is an A and this is a B, you cannot add them. If they were both A's, then you could add them. And that's going to be what applies here in F. Here we're multiplying two exponential terms. Notice that I have x's, but then I also have y's. So I can kind of combine the ones that match. So for my x's, I'm going to add the two exponents because it's being multiplied. And then for my y's, I'm going to add the two exponents. So my answer becomes x to the 9th and y to the 10th. Moving on down, G. Again, this is a division problem, so it looks exactly like letter B. When we divide, we are to subtract the exponents. So x to the 24th over x to the 13th. That is going to become x to the 11th. Now if I look at the y's, y to the 17th over y to the 7th, that's y to the 10th. And then at the very end, the z's. Z to the 8th over z to the 3rd, that's z to the 5th. Because these are all different bases, I cannot combine them anymore, so that is my answer. So those were all the kind of basic properties, and then here you have some where it starts applying different properties. For example, in letter H, there's parentheses with numbers on the outside. That means distribute, And ever since we started algebra, we've always said if you can distribute, you should distribute first. So this first term is going to become x to the 9th. Bring down the multiplication sign. And then 5 times 4 is going to be x to the 20th. Make sure you do not stop here. X to the 9th times x to the 20th, because they have the same base, I can actually add the exponents. So that means my final answer is going to be x to the 29th. Moving on to I, again, there's a little bit of distribution here. I'm only going to distribute to the top though, because only the top has the parentheses. So this is going to become x to the 15th over x squared y. Now, if you notice, I have two x terms on top and on bottom, so I'm supposed to combine those. So my new answer, since they're being divided, I'm supposed to subtract the exponents. 15 minus 2 is 13. And then there's nothing I can do with the y, so it's going to stay in the denominator. So the answer is x to the 13th over y. Lastly, j. We're multiplying three exponential terms here. These do have coefficients, and those numbers you do multiply. So 2 times 4 is 8, and then 8 times 3 is 24. And then if you go back and look at the x's, the exponent terms, because they all have a base of x, you can just add the exponents. So negative 5 plus 10 is 5. 5 plus 2 is 7. So the answer is 24x to the 7th. Hopefully that helps. If you need any more practice with exponents, exponent rules, just let me know. There's many things that I have that can help you. Moving on to number 2. Number 2 starts to address radicals. Letter A, simplify. There's nothing for me to do here. There's no operation, so they literally just want me to simplify the 75. So break it up. What are two numbers that multiply to 75? The two that come to mind are 25 times 3. 25 is a perfect square. The square root of 25 is 5. 3 is not a perfect square. It does not have a pair. So that means that my answer is 5 radical 3. Do remember that there are many ways to simplify. Yours might not match mine. Some students might do 15 times 5. In this case, you would have to break up the 15, which would get you 3 times 5 times 5. And then again, now you have a pair this time. So you're going to take that out as a 5. 5 radical 3 is what's left. Whatever works for you, not necessarily my method. In letter B, radical 48. What are two numbers that multiply to 48? The two that come to me are 4 times 12. I do not have any perfect squares, or technically I do. 4 is a perfect square. Square root of 4 is 2. But I also have to break up the 12. Two numbers that multiply to 12 are 4 and 3. 4 is another perfect square. 3 is left, as we talked about in the last problem. 3 does not have a perfect square. 3 is not a perfect square, does not have a pair, so that means that my answer is 4 radical 3. That is simplifying. In letter C, Now I do have operation, so they're asking me to subtract 7 radical 2 minus 4 radical 2. Because they have the same radical, I could combine the coefficients. So 7 minus 4, that's 3. But we do not combine the radicals. That stays as the same thing. If I had 7 radicals of 2 minus 4 radicals of 2, that means I have 3 radicals of 2. That should logistically or logically make a little sense. Next one, again, they gave me an operation. They have a plus sign. So what do I add? This has a 3, but there's a missing number here. We should know that there are invisible ones when there is no coefficient. So because the 15s are matched, 1 plus 3 is 4, radical 15. You might be wondering, 15 is a pretty big number. Can you reduce that? But the two numbers that multiply 15 are 3 and 5. Those are not perfect squares and do not match, so you would just multiply them back together. So cannot break down to 15. E. E is similar to D that we just did. Notice they both have plus signs. However, E is different in the fact that the radicals are not the same. So we don't just skip the problem. We have to ask ourselves, can we simplify or go through and check? Does it simplify? And if at the end you do get the same radical, you could combine them. So that is what I'm going to do. I'm going to start by simplifying this one. What are two numbers that multiply to 12? That's 4 times 3. Square root of 4 is 2, so I'm going to pull out a 2. 3 is not a perfect square, does not have a match, so my simplified answer for the first radical term is 14 radical 3. Now I have to simplify this. What are two numbers that multiply to 75? That's 25 times 3. 25 is a perfect square. Square root of 25 is 5. And 3 again, not a perfect square, not a pair, so that means this one simplifies to 20 radical 3. Bring down the plus sign. Now I could add these. Now they have the same radical. So when I add these, 14 plus 20 is 34 radical 3. F is right here. Again, you have to simplify. 8 radical 5, I cannot simplify that. There's no way for me to break up the 5, so I just got to break up the radical of 45. What are two numbers that multiply to 45? 9 times 5. 9 is a perfect square. The square root of 9 is 3. 5 is not a perfect square and does not match, so that means I am done simplifying. It simplifies to 3 radical 5. Bring down the first term as well as the subtraction sign. Now that they have the same radical 5, I could combine the coefficients. So the answer is 5 radical 5. G and H, this time the radicals are in parentheses next to each other. There is no operation. When things are in parentheses next to each other and no operation, that means they're being multiplied. They're telling me multiply these two radicals and then these two radicals. So in letter G, we normally multiply the numbers on the outside and the numbers on the inside. So there's invisible ones here. So on the outside of my radical, 1 times 1. On the inside of the radical, I'm going to put the 3 and the 15 together. If two things are under radicals, you can put them under one radical. Now I'm going to start simplifying the 15. Two numbers that multiply by 15 are 5 times 3. By factoring, we created a pair of 3's, so a 3 is going to come out. 5 is not a perfect square, does not have a match, so the 5 is going to stay on the inside. 3 times 1 is 3, 3 times 1 is 3. So the answer is 3 radical 5. Repeat the steps in H. Again, multiply the numbers on the outside. So 3 and 5. Multiply the numbers on the inside. And simplify as you go through. So what does the 8 break down to? Two numbers that multiply to 8, 4 times 2. Bring down the numbers that we had on outside. Now you'll notice 4 is a perfect square. Square root of 4 is 2. 2 and 3, they are not perfect squares, do not match. So you multiply them back together to get a 6. And you multiply all the numbers on the outside. 2 times 3 is 6. 6 times 5 is 30. 30 radical 6. A few more radicals here. I and J, and then K and L. These all look the same, but some of these are actually going to be a little different from the other. In the best case scenario, when you have two radicals that are being divided, you want to put them under one radical and ask yourself, can I divide them? For example, in this case, I wrote 150 and 3 under one radical, and I could divide these. 150 divided by 3 is radical 50. Now I do have to simplify that. Two numbers that multiply to 50 are 25 and 2. 25 is a perfect square, so it's going to come out as a 5. So that means my final answer is 5 radical 2. There was nothing else I could do. 2 is not a perfect square, does not have a match. J, again, I have two radicals. I'm going to put them together under one radical and ask myself, can I divide them? So I would plug that into my calculator if I need to, and in this case, I can. Radical 6. 6 cannot be simplified. 3 and 2 are not perfect squares, do not match, so that means the radical 6 is my answer. Let's check K. Let's see if this works with K. So I put the radicals together under one radical. 5 divided by 3. This time I cannot do it. I cannot divide 5 by 3 and get a whole number. So this is where we have to go in and rationalize. If I can't divide it, so what's the issue with this? The issue is not the radical 5, it's the radical 3. We are not allowed to have radicals in the denominator. Which means I'm going to multiply by the radical 3, because that's going to make a pair. So if you want to move on to this step, since I'm multiplying two radicals of 3, it's going to make a pair under my radical. And we know that I can take the pair out, so the radical is going to disappear. Now, what you learn in middle school, what you did on one side of a fraction, you also do to the other. So if I multiply the bottom by radical 3, I have to do the same thing to the top. In the top, now I have 5 and 3 under one radical. Those are not perfect squares. They do not match, so we would multiply them back together. In the bottom, as we said, we had a pair, so that's going to come out as a single 3 without a radical. And we're done. We did what we were supposed to do. We wanted to get rid of the radical in the bottom, and it's gone. Now there's just a regular 3. Letter I, radical 10 over radical 5, put them under one radical. Can I divide these? Yes. Get radical 2. Except this one didn't require any rationalizing because we could divide. Converting between radicals and exponential terms. I'm going to give you like a template here. Radicals and exponents are inversions of one another. That means you can change one to the other and then the other back. So as an example, if I have a to the b over c power, the way we change them, I read them as I write them. Some students memorize it as rules. So I start by reading a to the b power with a radical with a root of c. So some students memorize it as the top number becomes the exponent on the inside, the bottom number becomes the index, the root on the outside. So 7 to the 4/3 power. That's 7 to the 4th power with a radical of 3. X to the 1st power with a radical of y. That over. X to the 1st power with a radical of y. Number 4 is asking me to work backwards. Again, read it as you write it or use the rules however you interpret this. X to the 6th power with a root of 4. B might trip some of us up because there is a missing number. There's no number here now. Now, it's common for students to say, oh, all the invisible numbers are always 1, but that's wrong. There is actually an invisible 2. The explanation to that 2 is when I ask you what the square root of 25 is, you guys tell me 5. Why? Because in your head, you ask yourself what number times itself 2 times is 25. So that number tells you how many times you're multiplying. Now that we have this, we can write y to the 4th power over 2. Moving on from just rules onto exponential functions. It says the graphs represent exponential functions. Identify the key features of the graphs. I'm going to explain one the long way and then I'm going to talk about the shortcuts. Domain. The domain refers to the x values that a graph will touch. So my graph in red technically goes on forever. Because it goes on forever, that means it's going to hit every x value. This is -4, it's going to hit -5, -6, -100, -1000, and it's going to keep going. Down here, it's going to hit 2, and then it's going to hit 3, and then it's going to hit 4, because we're going this way. So 2, 3, 4, and it's going to keep going that way. So it's going to hit every number to the left, and it's going to hit every number to the right. In algebra, how do we say that something is going to hit every number? We say all real numbers. So that's my answer. All real numbers. That's the domain. Now for the range. The range refers to the y values. If you look, my graph is getting super close to 0, but it's never going to touch 0. There is an invisible line that our graph will never cross, never touch. But it does go down forever, so eventually it's going to hit negative, I don't know, let's say negative 6, negative 7, negative 8, eventually negative 100, negative 1000. Because it's going to hit every number downward, that means it's going to hit all the y values, so y that are less than 0. So we use an inequality to describe this range. The range, my graph is going to hit all the y values that are less than 0, that are below 0. Which makes sense because my graph is below the asymptote, below 0 on the graph. Y-intercept should be pretty easy for you guys. If you look at it, what's that number? That's 0, comma, negative 2. Last question is the asymptote. I drew that in right there. What's that blue dashed line, that imaginary line that our graph doesn't touch? That line is y equals 0. Now for the second one, I'm going to do more rules. In class, for domain, we said the domain is always going to be the same answer. For our class only, because it will change in Algebra 2, the domain will be all real numbers. All of my exponential functions that we draw in this class will go on forever to the left and to the right. So the domain is all real numbers. There's another one that doesn't change. We said the asymptote. The asymptote will always be in this class y equals 0. The range, you have two options. The option you saw in the one we just did, so y is less than 0. Or what happens when the graph is on the top, not on the bottom. In this one, the graph is on top. When the graph is on top, when the graph hits all the positive y values, we say y is greater than 0. My graph is above 0. Greater than means above. Y-intercept is that number, which is 1, 2, 3, 4. 0, 4. We're going to apply some of these rules to just regular exponential functions here. Given the exponential function, find the following. All right, I know two of these aren't going to change. Domain will always be all real numbers for our class, so I'm going to put those down already. I don't even need to think about it. And the asymptote doesn't change. Y equals 0. Y equals 0. Now, how do I get the y-intercept and range from a function and not a graph? Well, for that, we look at the a value, that number. That number is actually going to be your y-intercept. Your y-intercept is always going to be 0, comma, a. And you just have to take a out and put whatever a is in. So for this one, since a is 6, my y-intercept is 0, 6. Now, if I skip to 7 for a second, this one is missing the a. That x is on the 2. So technically, there's a number in the front. Even though we don't see it, there's an invisible 1. So that means the y-intercept, now that you see the a, is 0, comma, 1. For the range, you also look at the a. When the a is positive, your range is going to be y is greater than 0. Positive numbers are bigger than 0. So in 6, I have a positive 6, y is greater than 0. And then in 7, because a is positive 1, my range is the same thing, y is greater than 0. Let me give you an example that would have the other range. Let's say you have the function y equals negative 3, 4 to the x power. Because a is negative, this range would be y is less than 0. That is the key characteristics of exponential functions. Given the table, write an exponential function. Exponential functions have this equation. Y equals a times b to the x power, where a is the initial value, which means it's kind of like the y-intercept, which we just talked about. It is the y-intercept. A tells you what the y-intercept is. So the question you ask yourself, what is y when x is 0? And b, how do we get b? B is what we call the scale factor. What is the multiplication pattern? So if I look at table A, I'm going to start by labeling my variable A. So what is y when x is 0? Well, when x is 0, what's y? F of x. You use f of x in this table. So that's 0.5. Now for B, I have to find what's the pattern. How do they go from 0.5 to 1, 1 to 2, 2 to 4? Well, it kind of looks like they're doubling, multiplying by 2. So B is times 2, 2. Now that I have A and B, I can write the equation. Y equals A times B to the x power. I have to take A and B out. Y equals 0.5 times 2 to the x power. Just as a reminder, you will not see many decimals on the test. Most of it will be a fraction. So they would actually change 0.5 to 1 half. So you would see this answer. Y equals 1 half times 2 to the x power. Table B, what is the initial value? Again, when x is 0, what's y, or in this case f of x? So A is 3. Find B, what's happening to my table? 3 to 12, they're multiplying by 4. So B is 4. Now that I have A and B, I know that my equation needs to look like this. I just have to take A and B out and put the numbers in, so I'm going to do that. A goes away, 3 goes in, B goes away, 4 goes in, and I'm also going to write it out with parentheses. I'm going to pause the video here, and I will make a second follow-up video for the rest of the packet. Hopefully this helped with the first half. Again, let me know if you have any questions, if you want more practice with any of this. I know there was a Delta Math for the tables. You guys did really well on that. Exponential functions with the patterns, the rules, you guys did really good on. Radicals and exponents. Been about 2 to 3 weeks, maybe 4 for radicals. So there's a chance you might have forgot some of this. Hopefully this helped. And again, if you want more practice, you guys know that I have worksheets that I can give you with practice. Anything I can do to help you be successful. All right. Be on the lookout for the second video, which I will probably post tomorrow on Wednesday.